Hello everyone, today we are going to study an important topic in data structures, nonlinear data architectures. Until now, many of you may have learned about simple linear structures such as arrays, linked lists, stacks, and queues. These structures are called linear because data is arranged one after another like a straight line. But in real world computing, data is not always arranged in a straight line. For example, social media friends, road networks, web links, recommendation systems, priority tasks, and decision making systems are all connected in complex ways. So, today we will focus on two powerful nonlinear structures, graphs and heaps. Graphs help us represent relationships. A graph can show how cities are connected by roads, how people are connected in a social network, or how computers communicate in a network. Heaps help us organize data based on priority. For example, in a hospital emergency system, patients with more serious conditions should be treated first. In computer science, we can use heaps to quickly find the highest priority or lowest priority item. By the end of this lesson, you should understand why nonlinear structures are important, how graphs are represented, how BFS and DFS traversal work, how heaps maintain priority, and how heap operations such as insertion and extraction are performed. Let us begin by comparing linear data and nonlinear data. On the left side of the slide, we can see linear data. It looks like a sequence 1, 2, 3, 4, and so on. This is similar to an array or a linked list. In this type of structure, we usually move from one element to the next element. For example, if we have an array of 10 numbers, we usually access them using index positions. If we want to search through all elements, we may need to move step by step. This is simple and easy to understand, but it is limited. Now look at the right side of the slide. Here we have non-linear data. Instead of one straight path, there are multiple connections. One node can connect to many other nodes. This is closer to real life. For example, in a social network, one person can be connected to many friends. Those friends are also connected to other people. This cannot be represented well using only a simple line. Similarly, in a tree, one root node can have children, and those children can have their own children. This structure is hierarchical, not sequential. So, the key idea is this: linear data structures are good for simple ordered data, but non-linear data structures are better for complex relationships and optimized decisions. Graphs help us model relationships. Trees and heaps help us model hierarchy and priority. This is why nonlinear structures are very important in modern algorithms. Now we move into graphs. A graph is made of two main parts, vertices and edges. A vertex, also called a node, is a basic data point. In this slide, the letters A, B, C, D, and E are vertices. Each one represents an individual object. An edge is the connection between two vertices. For example, if A is connected to B, then the line between A and B is an edge. In real world examples, if vertices are cities, then edges may represent roads. If vertices are people, edges may represent friendships. If vertices are computers, edges may represent network connections. Next, we have adjacency. Two nodes are adjacent if they are directly connected by an edge. For example, if A and B have a direct connection, then B is adjacent to A and A is adjacent to B. A path is a sequence of vertices connected by edges. For example, if we travel from A to B, then B to C, and then C to D, that sequence is a path. Some graphs also have weights. A weight is a numerical value assigned to an edge. It may represent cost, distance, time, or difficulty. For example, in a road map, the weight can represent the distance between two cities. A degree refers to the number of edges connected to a node. If many edges are connected to one node, that node has a high degree. Finally, a loop is an edge that connects a vertex to itself. In the slide, we can see a loop near node D. This means the edge starts and ends at the same node. These terms are the foundation of graph algorithms. Without understanding vertices, edges, paths, adjacency, weights, degree, and loops, it is difficult to understand graph traversal and shortest path algorithms. Now that we understand what a graph is, the next question is, how do we represent a graph in code? There are two common methods, adjacency list and adjacency matrix. Let us start with the adjacency list. In an adjacency list, each node stores a list of nodes connected to it. For example, if node A is connected to B and C, we can write A points to B and C. This is very efficient when the graph is sparse. A sparse graph means there are not too many edges compared to the number of possible edges. For example, if we have 1000 people, each person may only be connected to 10 or 20 other people. In that case, an adjacency list saves memory because we only store actual connections. Now look at the right side, the adjacency matrix. An adjacency matrix uses a two-dimensional table. The rows and columns represent vertices. If there is an edge between two vertices, we mark the value as 1. If there is no edge, we mark it as 0. For example, if A is connected to B, then the matrix position for A and B is 1. If A is not connected to E, then the matrix position for A and E is 0. The advantage of an adjacency matrix is that checking whether two nodes are connected is very fast. We simply look at the matrix position. However, the disadvantage is memory. If we have many nodes, the matrix becomes large because it stores all possible relationships, even when many of them are 0. So the simple rule is this: use an adjacency list when the graph is sparse. Use an adjacency matrix when we need very fast edge lookup and the graph is dense. Now we discuss graph traversal. Graph traversal means visiting the nodes of a graph in a systematic way. There are two major traversal methods: breadth first search or BFS and depth first search or DFS. Let us understand BFS first. Breadth first search explores all nearby nodes first. It starts from one node, visits all its direct neighbors, and then moves to the next level. Imagine throwing a stone into water. The ripple spreads outward level by level. BFS works in a similar way. It expands outward from the starting point. BFS uses a queue. A queue follows the FIFO rule: first in, first out. The node that enters first will be processed first. Now let us look at DFS. Depth first search goes deep into one path before coming back. It starts from one node, chooses one neighbor, moves to that neighbor, then moves again to another neighbor, and continues until it cannot go further. After that, it backtracks. DFS is like entering a maze and following one path as deeply as possible. If the path ends, you come back and try another path. DFS uses a stack. A stack follows the LIFO rule: last in, first out. The most recently added node is processed first, so BFS is wide and level by level. DFS is deep and path by path. Both are useful, but they solve different types of problems. BFS is useful for finding the shortest path in an unweighted graph. DFS is useful for exploring connected components, detecting cycles, and solving maze-like problems. Now, let us understand BFS mechanics using the diagram. In the first step, we start from the root node, which is node A. We push node A into the queue. At this moment, the queue contains only A. In the second step, we pop A from the queue and visit it. Then we look at all unvisited neighbors of A. In the diagram, the neighboring nodes are added into the queue. This is very important. BFS does not immediately go deep into one neighbor. Instead, it collects all nodes at the current level first. In the third step, the queue works according to FIFO. The first node that was added will be processed first. So if the queue contains B, D, and G, BFS will process B first, then D, then G. After processing each node, BFS checks its unvisited neighbors and adds them to the queue. This process continues until the queue becomes empty. The main idea is that BFS finishes the current layer before moving deeper. This is why BFS is good for shortest path problems in unweighted graphs. If you are searching for the minimum number of steps from one node to another, BFS is a good choice. The time complexity of BFS is OV plus E, where V means vertices and E means edges. This means BFS visits each vertex and each edge at most once. Therefore, it is efficient and predictable. Now we study DFS mechanics. DFS also starts from a root node, for example, node A, but instead of using a queue, DFS uses a stack. In the first step, node A is pushed into the stack. Then DFS visits one unvisited neighbor of A. Suppose it chooses node B. Node B becomes the new active node. From B, DFS again chooses one unvisited neighbor. It may go to C, then E, and so on. This is why it is called depth first. The algorithm keeps going deeper and deeper along one path. If it reaches a terminal node, meaning a node that has no unvisited neighbors, then DFS backtracks. Backtracking means it returns to the previous node and checks whether there are other unvisited paths. The stack helps DFS remember the path. DFS is very useful in many problems. For example, it can be used to solve mazes, it can detect connected components in a graph, it can also help identify structural bridges and cycles. The key difference from BFS is this: BFS explores neighbors level by level. DFS explores one complete path before trying another path. In practical programming, DFS can be implemented using an explicit stack or using recursion. Recursive DFS is common because the function called stack naturally behaves like a stack. However, we must be careful with very large graphs because deep recursion can cause stack overflow. Now we move from graphs to heaps. Before understanding heaps, we need to understand the priori problem. A normal queue processes data in the order it arrives. This is FIFO, first in, first out. But sometimes the order of arrival is not the best order of processing. For example, imagine four tasks with processing times 5, 10, 3, and 2. If we process them exactly in that order, some smaller tasks may wait too long. But if we process the smallest task first, we can reduce the average waiting time. This is where a priority queue becomes useful. A priority queue does not simply process the first inserted item. Instead, it processes the item with the highest or lowest priority first. For example, in a hospital emergency room, the most serious patient should be treated before someone with a minor injury, even if the minor patient arrived earlier. In CPU scheduling, a system may process shorter or more urgent jobs first. In graph algorithms, priority queues are used in important algorithms such as Dijkstra's algorithm. But there is one problem. How can we efficiently find the highest priority or lowest priority item again and again? If we use a normal list, we may need to search the entire list each time. That is slow. So we need a better structure. That structure is called a heap. A heap is the structural mechanism behind an efficient priority queue. A heap is a special type of complete binary tree. There are two common types, min-heap and max-heap. In a min-heap, every parent node is less than or equal to its children. This means the smallest value is always at the root. For example, if the root is 2, then all children below it must be greater than or equal to 2. The root is the minimum value. In a max-heap, every parent node is greater than or equal to its children. This means the largest value is always at the root. So the difference is simple. In a min heap, the smallest value has the highest priority. In a max heap, the largest value has the highest priority. Now we also need to understand the structural rule. A heap must be a complete binary tree. This means all labels are filled from left to right. The last label may not be completely full, but nodes must be filled from the left side first. This complete structure is very important because it allows us to store the heap efficiently in an array. Unlike a generate tree, we do not need complex pointer connections. The shape of the heap allows us to calculate parent and child positions mathematically. So a heap follows two rules. First, the relational rule. Parent values must follow the min heap or max heap condition. Second, the structural rule. The tree must remain complete. These two rules allow heaps to support efficient priority operations. Now, this slide shows one of the most important ideas in heaps, array tree duality. Although a heap looks like a tree, we usually store it in an array. Why is this possible? Because the heap is a complete binary tree. Since all nodes are filled from left to right, their positions are predictable. In this slide, we use a dummy index at position 0. This makes the math easier. If a node is at position n, the left child is at position 2n, the right child is at position 2n plus 1. The parent is at position n slash slash 2. For example, if node A is at index 1, its left child is at index 2 and its right child is at index 3. If node B is at index 2, its children are at index 4 and index 5. This is very useful because we do not need to create actual node objects with left and right pointers. We can simply use an array or Python list. This makes heap operations faster and memory efficient. The main idea is this: a heap is logically a tree, but physically it can be stored as an array. This is why heaps are elegant and powerful. They combine the hierarchical meaning of a tree with the storage simplicity of an array. Now we study heap insertion. When we insert a new value into a heap, we cannot place it anywhere randomly. We must maintain both heap rules, completeness and heap property. The insertion process has three main steps: append, compare, and loop. First, we append the new value at the end of the array. This means the new node is added at the bottom of the tree in the next available left to right position. This maintains the complete binary tree structure. In this slide, the new value is 2. It is added at the bottom. Second, we compare this new value with its parent. Since this is a min heap, the parent should be smaller than or equal to the child. But here, the child value 2 is smaller than its parent, so the heap property is violated. Third, we swap the child with its parent. This is called the float operation or bubble up operation. After swapping, we again compare the new position with its parent. If the value is still smaller than the parent, we swap again. This continues until the value reaches the correct position. In the example, value 2 floats upward until the min-heap property is restored. So insertion starts at the bottom and moves upward. The time complexity is O or log n because the height of a complete binary tree is logarithmic. We do not compare with every element. We only move along one path from bottom to root. This is why heap insertion is efficient. Now let us understand extraction. In a min-heap, extraction usually means removing the smallest value, which is the root. But if we remove the root directly, the tree becomes headless. So we need a method to restore the heap structure. The extraction process has three steps: pop, promote, and sync. First, we pop the root. This removes the minimum value. Second, we take the last element from the array and place it at the root position. This maintains the complete tree shape because we remove from the end and fill the root. But now the heap property may be broken because the new root may not be smaller than its children. Third, we perform the sync operation, also called bubble down. We compare the new root with its children. In a min heap, the smaller child should move upward if the root is larger. So the root is swapped with the smaller child. After the swap, we continue comparing with the next children. The value keeps sinking downward until the heap property is restored. So insertion uses float upward, extraction uses sink downward. Both operations are efficient because they move along the height of the tree. The time complexity is log n. This is why heaps are very useful for priority queues. We can insert tasks efficiently and remove the highest priority or lowest priority task efficiently. Now we apply heaps to selection algorithms. Suppose we have a large unsorted dataset. We want to find the ith smallest element. One simple method is to sort the entire dataset. But sorting may be expensive if the dataset is very large and we only need one specific element. Instead, we can use a min-heap. First, we assemble the data into a min-heap. After that, the smallest element is at the root. If we call pop once, we get the first smallest element. If we call pop twice, we get the second smallest element. If we call pop I times, the final pop value is the ith smallest element. This is the main idea shown in the slide. For example, if we want the eighth smallest element, we pop from the min heap exactly 8 times. The eighth pop gives us the answer. This method is useful when we do not need a fully sorted list. We only need a specific ranked element. This idea is used in many real world systems. For example, we may want to find the top k search results, the smallest k distances, the highest priority jobs, or the most relevant recommendations. Heaps are very powerful because they allow us to repeatedly access the next smallest or next largest item without sorting everything from scratch. So the heap is not just a tree structure. It is also a practical tool for efficient selection and priority based computation. Let us now summarize the whole lesson. Today we studied two major nonlinear data structures, graphs and heaps. Graphs are relational webs. They help us represent arbitrary and organic relationships. For example, graphs can represent social networks, road systems, computer networks, web pages, recommendation systems, and dependency structures. In graphs, the main focus is connection. We ask questions like which nodes are connected, what path connects two nodes, what is the shortest path, which nodes are reachable, how strong or costly is each connection. To explore graphs, we studied BFS and DFS. BFS uses a queue and explores level by level. It is useful for shortest paths in unweighted graphs. DFS uses a stack and explores deeply along one path before backtracking. It is useful for connected components, cycle detection, and maze like exploration. Then we studied heaps. Heaps are prioritized hierarchies. They are used when we need fast access to the minimum or maximum value. A heap follows the complete binary tree structure and the heap property. In a min heap, the smallest value stays at the root. In a max heap, the largest value stays at the root. We also learned that heaps can be represented using arrays because of their complete structure. This allows us to calculate parent and child positions using index formulas. We studied two important heap operations. Insertion uses the float operation, where a new value moves upward. Extraction uses the sync operation, where a replacement value moves downward. Finally, we saw that heaps can support selection algorithms, such as finding the ith smallest element. So the final message is this: when data is simple and sequential, linear structures are enough. But when data has relationships, priorities, networks, hierarchies, and complex connections, we need nonlinear structures. Graphs help us understand relationships, heaps help us manage priority. Together, they allow computer systems to model real world complexity more effectively. That is the main concept of nonlinear data architectures.